This is the second of 4 videos in Module 1, Introduction to Biochemistry. In this video, Review of Energy and Thermodynamics, I'll be talking a little bit about some of the properties of heat and power that are related to biochemical reactions and biochemical molecules. Okay, so living organisms are an open system. They exchange matter and energy between the system and their surroundings. A thermodynamic system can be a single, simple chemical reaction or an entire organism. And so in this case, we're talking about living organisms, which are interdependent on the environment. They exchange energy and matter with each other and with the environment. So organisms derive energy from their surroundings by either taking up fuel or chemicals in the form of glucose, or by absorbing energy from sunlight to create their own glucose, as is the case with plants. In fact, the ultimate source of almost all energy used by organisms on our planet essentially comes from the sun. Since plants are able to absorb energy from sunlight to create glucose, and we are able to consume that glucose to create our own cellular energy. Organisms convert energy from either of these two sources to produce some type of work. How we do it is we convert our chemical fuel to another type of chemical fuel called ATP. As a byproduct of that, we return some energy to the surroundings in the form of heat. And so one of the byproducts of cellular respiration, which we'll talk a lot about towards the end of the semester, is heat. And then we also release carbon dioxide in water as product molecules. And these products, carbon dioxide, water, and heat, are less organized than the starting fuel, which is glucose. And so what I'm getting at is this idea of entropy. And so all of the energy that you see from the beginning through the middle and to the end remains constant. So the total amount of energy is constant. It's just that we transform it into different types of energy, be it electrical energy, chemical energy, or kinetic energy. Entropy, however, tends to increase as we go through these processes. As we derive energy from surroundings and absorb heat from the surroundings, the end products of these biochemical reactions are less ordered than what we started from. And so I'm going to talk about how energy is transformed through biochemical systems and how entropy changes throughout these processes. So in biochemistry, we're concerned with 2 laws of thermodynamics. The first law of thermodynamics, which is the conservation of energy law, and the second law of thermodynamics, which is things in the universe tend towards a state of chaos or entropy. So first I'm going to talk about this one. The first law, the conservation of energy law, states that the energy in the universe remains constant. Energy cannot be created nor destroyed, but it can change forms. And so we can convert motive power into electrical power, as is the case with water flowing over a dam. We can convert solar energy to cellular energy, as is the case for plants that do photosynthesis. We can convert cellular energy into some type of mechanical energy, as is the case with using ATP to drive some type of enzymatic reaction that allows you to move your body. Sound waves are changed into vibration waves through the ear as through the process of hearing. Your nerves convert electrical signals and ionic signals to chemical ones. And so many biochemical reactions convert and change the energy the form that energy takes, but it won't destroy it, nor will it create it. Second law of thermodynamics states that entropy, or a measure of a system's disorder or randomness in the universe, increases. And so chemical reactions and other types of energetic reactions will tend towards a state of chaos or increased entropy. And so, for example, organisms extract free energy from the surroundings. So we extract glucose from our surroundings. And then we oxidize that with oxygen. The end products that are formed are carbon dioxide and water, and also heat. And so that's what's being pictured down here in these boxes. We start this chemical reaction of cellular respiration with 7 molecules, 6 molecules of oxygen and 1 molecule of glucose. At the end of this biochemical reaction, we end up with 12 molecules, 6 molecules of carbon dioxide and 6 molecules of water. And so this box represents more entropy or more chaos, less order, because if there are more molecules in this space, these molecules can occupy this space in a greater variety of ways than can these molecules. So think of it as these 7 molecules can exist in different areas, and these 12 molecules can exist in different areas, but the amount of differences where they can exist and the different patterns they can create in this space is more diverse. So there's more chaos in this space. The example I like to give is that of my kids' playroom. So this is my kids' playroom. This is the playroom before, when they wake up in the morning, before they get at it, and this is the playroom at the end of the day. And so, all night, there's lots of order here, lots of disorder here, and so everything tends towards this state of chaos here. That's definitely true in my house. In fact, my dad, when I was growing up, used to say to me, don't fight the second law of thermodynamics. Don't bother cleaning your room, because everything's just going to end up towards a state of entropy anyway. I didn't think I really understood or cared too much what he was telling me then, but I understand it now. And so let's summarize these two thoughts. So again, naturally occurring processes or spontaneous ones will always proceed towards the state with the least potential energy, or ones that release energy. The second law, which is related to entropy, naturally occurring processes or reactions must increase the disorder in the universe. And so if a biochemical reaction is to proceed spontaneously in our bodies, it has to satisfy these 2 laws, which means the end products must release energy into the environment, and the end products must increase the amount of disorder in the universe, or increase entropy. And so with using these 2 laws, thermodynamics will tell us if a reaction is possible and whether or not it will occur on its own without the input of energy. Okay, so let's talk about how we represent energy in a biological system. Gibbs free energy represents the usable amount of energy in a biological system. And so Gibbs free energy is related to 2 different properties: enthalpy, or the heat content of the system, and entropy, or the measure of disorder in a system. The transfer of energy in a single reaction or in a single organism can be described by these 3 different quantities: Gibbs free energy, enthalpy, or H, and entropy, or S. How students in the past have remembered which symbol stands for which is that H can stand for heat, and S can stand for shambles, or a state of disorder. If the amount of heat if heat is released into the surrounding environment, that would be considered a favorable reaction and would proceed spontaneously without the input of energy. And so therefore, if you were to take the amount of heat after and subtract it from the amount of heat before, if we're going to release heat into the environment, this overall delta H would be negative, a negative number. And so a negative delta H indicates that the reaction would be favorable. Over here, we have to increase the amount of entropy in the system. So we're decreasing order, increasing disorder. And so the amount of entropy after minus the amount of entropy before the reaction took place would represent the delta S. And in this case, a positive number increases entropy and therefore would be considered a favorable reaction. And so considering all these 3 terms together help us to determine whether or not a biochemical reaction is spontaneous or occurs without the use of energy, without the use of ATP, or not spontaneous, and would require the input of energy in some way. Let's take a little bit of a closer look at enthalpy, or this idea of releasing heat into the surrounding environment. So again, will a biochemical reaction release heat into its surroundings or absorbs heat from the surroundings? And if energy is going into a system, then enthalpy increases. If energy is going out of the system and being released, then enthalpy decreases. And so remember, the goal here is to release energy into the environment. So this reaction here would be favorable. So some of the bonds in the reactants of a chemical reaction, so everything on the left side of an equation, are broken, and then new bonds are made to form the products. So here we have to break a bond, and then we have to reform bonds to make products. And so this would be the product, and these are the reactants here. And this would be some kind of transitional state in the middle. It costs energy to break bonds. Energy has to be absorbed from a system to break a bond. But when new bonds are created, energy is released. And so what we're looking for is, so both are happening in any biochemical reaction where we have energy in and energy out. It's just that the energy out has to be greater than the energy in. And that will tell you whether or not a reaction is spontaneous. So spontaneity depends on the balance between bond making and bond breaking steps. Let's take a little bit of a closer look at entropy. So again, does our biochemical reaction increase or decrease entropy? And the goal is, or for a spontaneous reaction, entropy would increase, so disorder increases. So when entropy, or in biochemical reactions, entropy increases when mass increases, when molecules melt and go from a solid to a liquid state, when molecules evaporate and go from liquid to a gaseous state, as molecules sublimate, as liquids or water or solids or liquids dissolve in water, and also entropy increases with higher chemical complexity. Since as you start to link more and more atoms onto a molecule, there's more interference and more steric hindrance between functional groups on a very large and complex molecule. And so that would represent increase in disorder. Entropy would decrease for some of these opposite reactions. So as gas is dissolved into water, or as molecules move from a liquid to a solid state, or as substances become more brittle or become less soft. So this means that free energy, or delta G, is a measurement of enthalpy, or the change in heat in the system, and also entropy, or the change in disorder. And this is also related to temperature. And so we can represent the overall free energy change by this equation: delta G equals delta H minus temperature times delta S. And for a process to occur, the overall delta G must be a negative number. That doesn't necessarily mean that both of these are favorable, that delta H is negative and delta S is positive. We can sort of play around with this side of the equation using temperature as a factor. But at any rate, these two values together must equal a negative delta G for a reaction to proceed spontaneously. Free energy of the products must be therefore less than the free energy of the reactants in order for delta G to be negative. Okay, so let's take a look at different types of delta Gs and how that relates to biochemical reactions. So free energy calculations will tell us whether or not a process occurs spontaneously or not by looking at the different values that I had just mentioned before. So if delta G is greater than 0, so a positive number, the reaction cannot happen spontaneously on its own. What this means is the free energy represented by the products is much greater than the energy represented by the reactants, and therefore this overall number will be a positive number. This is referred to as an endergonic reaction and requires the input of energy to proceed. So this means for a reaction that has a positive delta G, energy must be absorbed from the surrounding environment. If the delta G is a negative number or less than 0, the reaction will happen spontaneously on its own without the input of energy, and therefore energy is released into the surrounding environment. We call that an exergonic reaction. So endergonic reactions are non-spontaneous, exergonic reactions are spontaneous. If there's no change in the energy of the system, and then no net change really, so if the amount of energy being released equals the amount of energy being absorbed, then delta G is 0, and this represents the reaction at its equilibrium state. And it's really important to note that delta G will not indicate how quickly a reaction will proceed or how fast it happens. It will only determine whether or not it can occur on its own. And so many different biochemical reactions in our bodies will proceed spontaneously, but would take so long to complete that we would essentially be dead before these reactions would be allowed to finish. And so that's what enzymes will do. We have specific enzymes that will speed up the rate of a reaction, but will not change the overall delta G of the reaction. So enzymes are useful for very, very slow moving spontaneous reactions, but it will not change a non-spontaneous reaction into a spontaneous one. We'll talk way more about enzymes later in the semester. One biological example that I can give you of something like this is that of cellular respiration. And so the overall chemical reaction for cellular respiration is glucose plus oxygen yields carbon dioxide and water. Specifically, one molecule of glucose plus 6 molecules of oxygen yields 6 molecules of carbon dioxide, 6 molecules of water, and then also heat and ATP, which is the overall end goal. And so if cellular respiration of glucose we need to be able to create ATP or make a bond through the process of oxidizing glucose. And so what happens is through the process of cellular respiration, we have to be releasing more energy into the environment than we absorb in order to provide the driving force for ATP production. And that's exactly what happens with cellular respiration. Again, far more on that later in the semester. So here's a chart that I've created here to sort of help you understand how delta H and delta S can affect delta G in different ways. And so I had said before that a negative delta H is what we're looking for. We're trying to release heat into the environment. And a positive delta S, or an increase in entropy, is also would be favorable. And so the best case scenario is if both of those things are true. Delta H is negative, delta S is positive. Where we release heat into the environment, we increase disorder. And therefore, this reaction would be spontaneous at every temperature, and T doesn't really come into play. Delta G is always negative in this case. The opposite situation would be a completely non-ideal situation where delta H is positive and the system is absorbing heat from the environment, and delta S is negative, and the products represent more order than the reactants. And so we've decreased entropy in the system. This would be a non-spontaneous reaction at any temperature. So again, temperature doesn't come into play if delta H is positive and delta S is negative. This would be a non-spontaneous reaction at any temperature. Delta G is therefore positive. However, if we consider sort of an ideal delta H and a less than ideal delta S, or a less than ideal delta H and an ideal delta S, then we can change or we can make these reactions spontaneous by adjusting the temperature. This means that the Gibbs free energy equation and Gibbs free energy in general is dependent on entropy, is dependent on temperature, is dependent on all of the other things that would be true for a biochemical or a chemical reaction at equilibrium. Oops, sorry about this. That's going to make more sense in a moment. So let's walk through this. The entropy of a substance increases with its volume. So think of it this way. If there's more space in the system, there's more options for a molecule to exist in one spot. There's just more places that that molecule can take up space if there's more space to take up. And so the entropy of a substance would increase if the volume of the system increases. Entropy, or delta S, is therefore a function of concentration. If we're talking about the presence of a molecule in a specific space, then what we're really talking about is molecules per unit space, or concentration. Entropy increases as concentration is reduced. So reducing the volume increases the concentration, which would be less entropy. Increasing the volume decreases the concentration, and therefore you have more entropy. So if entropy changes as a factor of concentration, Gibbs free energy must also change as a factor of concentration, since these values are related to each other by the Gibbs free energy equation. So if the free energy change of a chemical reaction depends on concentration of the reactants and the products, then we can examine biochemical reactions and whether or not they're spontaneous or non-spontaneous, and adjust these reactions based on the concentrations of the reactants and products. Okay, so this is going to make more sense with an example. So I'm going to give you two different ways in which we can make chemical reactions more favorable. The far majority of life's chemical reactions are thermodynamically unfavorable. So how on earth are they occurring in our bodies then? There's two different ways that we can do this. So the first method is unfavorable reactions can become favorable if you adjust the concentration of reactants and products, since the Gibbs free energy is related to entropy and entropy is related to concentration. And so we can examine this step right here, which is one of the steps in glycolysis. One of the steps in glycolysis yields this product here, DHAP, or dihydroxyacetone phosphate. This has to convert into one of its isomers, glyceraldehyde 3-phosphate, in order to continue down the pathway. The next enzyme in the pathway will only bind to this molecule, but will not bind to this one. However, all of the steps before this will yield this molecule, and so we have a problem here. The problem is that this molecule will not spontaneously convert to this molecule because this reaction, moving in this direction from DHAP to GAP, is endergonic. It has a positive delta G. In fact, this reaction tends to proceed in the reverse, where from GAP to DHAP. And so how do we overcome this problem? Okay, so the issue is here that these biochemical reactions are not happening in a vacuum under standard conditions. They're happening under biological conditions. And so we can adjust our delta G, or delta G here is really referred to as a value called delta G naught, which is calculated from the Gibbs free energy equations, assuming all normal standard conditions. So standard pressure, standard temperature, and all of that. However, like I said, these biochemical reactions don't occur under standard conditions. They occur under variable components, under variable conditions. And so we have to recalculate delta G based on those variables. So delta G naught, this would be delta G naught. But again, we have different temperatures to consider. We have different concentrations to consider. And so what we can do is sort of follow Le Chatelier's principle. When any system at an equilibrium is subject to change in concentration, temperature, volume, all of these standard conditions, and then the system can readjust itself to counteract that change, that perturbance. And so what we can do is, if you decrease the concentration of this molecule, that will automatically make this molecule more abundant, and then the reaction will tend more towards DHAP to GAP. And so basically what we have to do is find a way in our bodies to make GAP scarce. And so this is why glycolysis is part of a pathway, a biochemical pathway. So as I mentioned before, this molecule is the one that's allowed to continue on in the remaining, I think, 5 steps of glycolysis. This one is the result of the previous 5 steps, and we have to convert between these two. The moment that this molecule is made, it's almost immediately consumed by the next enzyme in the pathway. And so because GAP is so readily consumed, the concentration of GAP is almost always really, really small, really, really low. And so that means that DHAP is always much higher than GAP. And so delta G can be sort of adjusted, or this can be this can be a more spontaneous or favorable reaction if we front load the reaction with lots and lots and lots of this, and that it will push the reaction more from DHAP to GAP. So therefore, delta G can be made negative by adjusting the concentrations of reactants in products. And this is the basis of why biochemical reactions are often in pathways. So if these were independent reactions and not in a biochemical pathway, then we wouldn't be able to take advantage of Le Chatelier's principle to get this reaction to move forward. But because GAP is consumed almost immediately after it's made, the concentration of GAP is almost always low. Therefore, DHAP is always high, and the reaction usually proceeds from DHAP to GAP. Okay, so what if you can't adjust concentration? What if that's not an option? And so there's a second method in which we can proceed to make biochemical reactions more favorable. So unfavorable or endergonic reactions can be coupled to more favorable ones and sort of cancel out the positive delta G of an unfavorable reaction. And so let's take a look at other parts of glycolysis. So the first step of glucose oxidation is the conversion of glucose to glucose 6-phosphate. We are creating a bond here. We're taking a phosphate group and adding it to glucose. This is not a favorable reaction. This requires the input of energy, and therefore our delta G is positive and therefore requires the input of energy. And so this reaction would not proceed on its own. And as a consequence, we'd never be able to trap glucose in our cells by adding a phosphate group, which is a really critical first step of glycolysis. ATP hydrolysis, however, is a highly favorable reaction. So when we turn ATP into ADP and phosphate, so we're breaking a bond here, the delta G of the reaction is negative. And so lots of energy is released into the surrounding environment. We have a very negative delta G. And so what we can do is couple this reaction to this reaction, combine the two. So if these reactions are coupled in the cell, then the overall net change in delta G is negative. And so this is actually a really interesting feature of glycolysis. When you look at the first few steps of glycolysis, you have to use ATP in order to get that to happen. And so the first couple steps in glycolysis are actually endergonic reactions. However, we consider the overall glycolysis pathway to be exergonic, or release free energy into the environment. And the reason is because if you look at all of the reactions all together, the overall delta G of the entire pathway is negative, even though some of the individual reactions within the pathway are positive. Because they're all coupled together, we end up with a more favorable reaction. So let's link this to a biochemical property. Here we have some amino acids that are all single amino acids. Obviously, this represents a more chaotic environment versus a protein or an amino acid sequence, which is more highly ordered. This is an endergonic reaction. Going from multiple amino acids to a single protein actually increases order or decreases entropy, and therefore this reaction is not favorable. It's an endergonic reaction. However, if we can couple the use or the hydrolysis of ATP to the creation of these bonds, peptide bonds, then overall, by coupling these two reactions, an unfavorable process with sources of this unfavorable process is made favorable. And so we can couple thermodynamically unfavorable process of going from lots of amino acids to a single protein with sources of high energy like ATP hydrolysis. And this allows us to create large polymers of proteins. Okay, so let's talk a little bit about equilibrium. So in any chemical reaction in a closed system, you can eventually reach what's called equilibrium, where there's no net change in the overall energy released or absorption. And so equilibrium in our systems cannot really be reached. So equilibrium is no change in concentration of reactants or products. It's the steady state, no change whatsoever. However, we are constantly ingesting high enthalpy, low entropy nutrients and converting them to low enthalpy, high entropy waste products. So we're continuously ingesting these nutrients by consuming food, water, and all that stuff, and converting them to waste products. And so because we're constantly perturbing the system and changing concentrations of reactants, living organisms can only reach equilibrium when we die. And so that's when we become a closed system. There's no input in the system anymore because you're not able to ingest anything when you are deceased. And so we become a closed system. However, we can maintain some type of homeostasis in our bodies, which are sort of like a pseudo equilibrium for biochemical reactions. Our system is reacting to changing in concentrations and properties in order to restore our steady state. So every time we perturb the system, there are other systems in place to try to return that system back to equilibrium. It's just that we're constantly perturbing it. And so we don't really maintain a constant equilibrium. We sort of oscillate around a steady state. So think of body temperature, how it changes throughout the day, and things like blood sugar, how they change throughout the day.